Hi,
Hello,
sir.
Amy. How are you doing?
I'm good, thank you. How are you?
Good, good. So, we are learning calculus. How do you find this experience of learning calculus, Amy?
Really good. I actually started off dreading it, absolutely kind of like scared of it. But you obviously led the way, and it hasn't actually been that bad. It started off with a few bumps, but I think all it needs is like practice. And at the beginning, when you start like asking so many questions, like why am I doing this? Like, what's the point? Later on, obviously, when more and more topics build up, it all starts making sense, and like you start using those concepts. So like just bear with asking all the questions at the start.
That's true. We'll take up a new topic today, Amy. We have learned about chain rule. We have done optimization questions, kind of. We've done
Yeah,
range questions also. And you realize we also did some local maximum and local minimum questions, right? Uh,
yeah,
Now, in those local maximum, local minimum questions, to find your maximum minimum point, we actually analyze the first derivative, right? So if it changes from increasing to decreasing, we hit a maximum. And if it changes from decreasing to increasing, it hits a minimum, right?
yeah,
At this point, which normally we'll say local maximum and local minimum, right? Because for many graphs like x cube and all, the extreme values are going to one infinity to the other, right? So in between, we'll say those are not the absolute maximum minimum points.
yeah,
We also noticed that to find the local maximum minimum, we could adopt another method, and that was we could analyze the first derivative to find the stationary points. I prefer to write them as critical numbers, so critical points, and then we could do the second derivative. If we do the second derivative and we get second derivative as positive, positive means you can hold, concave up means minimum, right? So if the
yeah.
second derivative is positive, it is a parabola kind of thing going upwards, you hit a minimum. If the second derivative is negative, things falling down, in that case, you hit a maximum, correct?
That's
So
correct.
that was the other concept which we learned about the local maximum and local minimum. Correct?
Hmm.
Now you realize in most of the questions, especially the real life situations, for example, we'll have time and we say time is greater than equal to zero. Perfect. We'll say
Hmm.
this experiment is performed for a period of 10 days. There is a boundary. Get the idea? So most
Yeah,
of the time we are working in a time frame or some restrictions. It's not like from one infinity to the other infinity. Right? It's not.
yeah,
So in most cases, we are always working with a boundary. So in calculus also, because it is all understanding the real life situations, modeling them, that is all calculus is. So we
yeah.
have actually now modeled real life situations with the help of another concept, which we are saying working in closed intervals. So when I say closed intervals, I really mean that we have both ends closed. We know from where to where, and these two things are included in our interval.
All right. Okay.
One of them is not included, then it is not closed, right?
All
For
right.
example, if I say t greater than 0 but less than equal to 10, that is not closed because we don't know the starting point.
Oh, yeah, yeah.
But if
Makes
I
sense.
say t greater than equal to 0 and less than equal to 10, it is closed. You understand the
Oh,
fine definition of closed
yeah.
now? Square
So both
brackets, both
included.
sides square brackets, both included. So if that is the case, we have a very simple way of finding absolute maximum and minimum, right? So you'll be surprised to see some examples for the first time. Let me ask you a question. If I have a straight line, can I have an absolute maximum or minimum?
Um, no.
No, because y equals to x goes forever, right?
Yeah.
But if I say the straight line is within the interval from, let's say, -1 to +1, do we have x absolute value of maximum and minimum?
Yeah, because you've put a little bit of a restriction. So that one would be the max, or like
That's
that.
right.
Yeah, the other way.
We have a segment now to work with. Now, this
Yeah.
particular segment has endpoints, which, one is minimum, absolutely minimum point, and the other one is the absolute maximum. That is the basic
Mm.
concept, right? And with this basic concept, let's see how to solve questions and how do they make things very simple for us. Soon you'll realize that many times we may not even analyze the first and second derivative to find our absolute maximum minimum. Okay,
All
so that's
right.
the topic for the day, and I hope you love it.
I know I will.
Actually, it's very simple, right?
Yeah.
Okay, let's see whether it really works. Let me just share with you uh, the the playlist. Okay, so there we go. We're talking about absolute maximum minimum. Okay, I think that's the correct one. Okay. So here, can you see the screen, please?
Yeah.
What is the title?
Absolute extrema in restricted domain.
Perfect. In restricted domain, two words. So absolute means total maximum or extreme value, right?
Yeah.
Extreme will be used for both maximum or a minimum value. Restricted domain means we know the interval from where to where. Okay,
All right. Yeah.
that's what it means. Now we'll learn the concept of absolute maximum minimum. Then there is a theorem which is called the extreme value theorem. We'll understand this particular theorem. It
Mhm.
only works with the closed interval. So we'll say closed interval method. We'll have applications and a practice test for you at the end of this exercise. So here on the screen, there are four different graphs. One, we have a parabola, which opens upwards. We have a straight line, minus infinity to negative infinity. Then we have a kind of cubic function graph, which is restricted uh, at two fine ends, a to d. And then we have 1 over x, a reciprocal function graph without any restrictions. Now, the
Mm.
question for you, Emmy, is you need to identify absolute and local maximum minimum points on these graphs, right? Let's
Mhm.
begin with the very first graph here. Do you have absolute maximum or minimum point here?
We have an absolute minimum.
Yes.
That's
You
the
have,
point that you've highlighted.
you are right. We have absolute minimum, but we don't have absolute maximum because it's going to positive infinity. Second, this absolute minimum is also your local minimum. Do you see that part?
All right. Yeah.
Absolute minimum is also your local minimum because in the small vicinity, it is the lowest level, right? So at times, the local values of maximum minimum could be also absolute maximum or absolute minimum. Yeah.
Yeah.
Now, if we have a continuous function, then it is not necessary to have even a local maximum minimum or something like this. You're right. Forget about absolute maximum minimum. Example,
Mm.
straight line. Now see what happens. I could have a cubic function which goes from minus infinity to plus infinity. In that case, I do not have any absolute maximum or absolute minimum values.
Yeah.
However, as soon as I cut it within a defined interval, I have local maximum minimums and I have absolute minimum maximum also. Do you see that?
All right. Yeah.
Perfect. So
Mm.
whenever you have a constraint interval, which is restricted from both the sides, always you're going to have absolute maximum and absolute minimum value.
Oh.
You could also try on a line. If I just cut this from here, for example, this is your absolute minimum, absolute maximum value, correct? So for any function, if we have a restricted domain, both endpoints included, in that case, we'll definitely have absolute maximum and absolute minimum value, correct?
All right. Yeah.
Now, here is a function, and this function is very different from the other function. Can you tell me the difference between this particular function and the rest?
That one's not continuous.
Yes. This one is not continuous. So another restriction while working with extreme value questions is that within the restricted domain, your function should be continuous.
Oh, okay.
That is why I given that figure here. It has to be continuous within that particular frame, right? Only then you'll have absolute maximum and absolute minimum for sure.
All right. So that one doesn't have absolute max or min.
Yeah. You might sometimes have, but it is not for sure, okay? So
All
when we
right.
find a theorem, we say always true, right?
Yeah.
So when we say always true for absolute extrema restricted domain, then both the endpoints are contained and it is continuous in between.
Okay.
Plus, you have understood all the constraints now. So now here is the theorem for you, which is called the extreme value theorem. So Amy, can you read this theorem for me?
Yeah. So if f is a continuous function on a closed interval a, b, with square brackets, then f will have an absolute maximum value, f of c, and absolute minimum value, f of d, at some critical numbers c and d in the interval a
Closed
and
interval
b.
A and B. Got it? So in short, whatever I was saying has been summarized here in the form of a theorem, and that's a very important theorem. And there are some very critical words here also to understand. If f is a function, second is continuous function, very important. Continuous function, not like 1 over x shown there. Closed interval means you have square brackets. Closed intervals, right? Continuous within the closed interval. Then and only then f has absolute maximum value. At some point, we are saying f of c, and
Yeah.
absolute minimum value. At some point, we are saying d. Is that clear to you?
Yeah.
These points c and d will be within this interval, closed interval ab. Got the idea?
All right.
That's what it is. Simple, right? Now,
Yeah.
the last example, I just extended it a bit more and pulled down the point A to a local, the absolute minimum, right? So as you can see here, I have this cubic function, and you can see it has local maximum minimum, absolute minimum, and absolute maximum values, correct?
Mhm.
It is a continuous function contained within a restricted domain where both limits are included, right? Solid
Mm.
filled in circles included. Now tell me why in the second figure we do not have absolute maximum and absolute minimum value.
Because there's a jump discontinuity.
Perfect.
The
Second,
holes. So it means it's not a closed interval.
second, closed interval, right? So both the things are very important to notice. Not a closed interval, so we will not apply extreme value theorem there, okay?
All right. So could I just ask a quick question?
Sure.
With the cubic function, so imagine if we went so you go up and then you go down and then you go up and then you go down again,
Yeah.
and that local minimum, if it's the same like
Yes.
point as that other local minimum, can you say there's two local minimums?
Yes. Yes.
Oh, okay.
Definitely.
Just wondering.
Sure, we could. I could have had this extreme value somewhere here itself, for example, as you're saying. I could have
Yeah,
an interval which ends here. Is that clear to you?
yeah.
So yes, that local, which is minimum, will become absolute minimum also, right?
Oh,
You
okay.
may say, well, the y value. When we say minimum, I should write value. So let's focus on this word also, value. Y value is same. Do you see that? Because horizontal
Yeah,
line,
yeah.
all those points. So when you say maximum value, y value. So whether there are 10 points, it doesn't matter. The value of y is same.
Oh,
Got the idea?
okay. So
So
maximum value, we're looking at the y value,
y
nothing about the x. Oh,
value, correct? So that is very important. So when you say what is the maximum cost of this thing, don't worry whether you are buying 10 items or 4 items, you have to pay the maximum cost. Got the idea?
oh, right. Yeah.
Yeah, that's critical, and it's a very good question. Many times when I type in, I just forget to write value, right? So while typing, I make many mistakes. This is one of those mistakes. But fortunately, I found that value there. Now, here is an example which will actually help you understand the whole concept and also appreciate the simplicity of this particular rule, how it helps us to find, the extreme values, correct?
Mm.
So the question here is, Find the maximum area of a rectangle that can be inscribed in a semicircle of radius 10 centimeters. Simple statement. So we have a semicircle given to us, which is right there, right?
Mm-hmm.
Within that semicircle, we could make many rectangles, but we are interested in one particular rectangle which could give us the maximum area. Right? It makes sense because if you have a semicircular piece of metal, you want to cut and make it rectangular, you'll like to have maximum area, right?
Yeah.
So it is a very practical question. Now, how do we solve such a question? Now, you could have solved without extreme value theorem also, but here we will see how to optimize using extreme value theorem. Okay.
Okay.
So, this is also a very important question. We are considering one shape inscribed in another shape. A rectangle is inscribed in a semicircle. It could
Yeah.
be similar to a rectangle inscribed in a circle, also the same approach. Okay. The
All
only
right.
thing will be the area will be doubled, but same approach. And so the approach which we are going to adopt here applies to many questions where things are like inscribed in another geometrical shape, right?
Mm-hmm.
So consider this solution as a very general solution for many difficult questions where we could have within a sphere we could have a cone. You understand? 3D
Mm-hmm.
and be difficult question, but the approach is kind of similar. Okay, so whatever we do is something like this. Since we want to inscribe a rectangle in a semicircle, you should maximize and take a point on the semicircle itself. So the
Yeah.
idea is pick a point on the semicircle. Any general point, we are calling this as P equals to XY. Now, as soon as I write P equals to XY, then that means that this is Y value, right? And this is my X value.
Yeah.
So I have defined my rectangle saying the width of the rectangle is y, but the length is 2x, right? X and x. The length is 2x, and therefore I also have the area, which is multiplication of x and y. 2 times x is my length, and y is my width. So the area is 2xy. Clear?
Yeah.
Now, we need to relate x with y some way or the other. And in that case, we know we are given the equation. It's a semicircle, means x square plus y square is radius square, which is 10 square. And so I could write down y equals to square root of 100 minus x squared. I'm taking positive values here since we are talking about a semicircle above the x-axis. Correct?
Mm-hmm.
As soon as I do this step, I know that we're talking about this point which is only within minus 10 to plus 10. Restricted.
Correct. Yeah.
In all our application questions, we'll actually have restricted domain. The challenge will be to define this restricted domain always. You understand?
Oh.
That's a challenge sometimes. So we easily can say that the value is from minus 10 to plus 10. Okay? That is the x value.
Wait, how did you know it was? So I get that the radius was 10, but how did you know it went to minus 10?
Okay. Your
Does it have
point
to be
P is
symmetrical?
here, right? You could take point P anywhere on the circle. So
Mm-hmm.
the x value could change from plus 10 to minus 10.
Wait, was that semicircle, did you draw it, or is it given in the question?
Find the maximum area of a rectangle that can be inscribed in semicircle.
Oh, so they give you that.
Into rectangle and semicircle. Correct?
Do they give you that diagram, or did you?
No, I have drawn it. They might give you, but assume they have not given you diagrams, okay?
Oh, right, okay.
Yeah, assume they will not give you, okay? Most of the optimization questions, rate of change questions and applications, they will not give you diagrams.
Oh,
They will
okay.
give you a formula, right? They'll say volume of a sphere is this, volume of a cone is this, surface area is this, equation of circle, semicircle is this. They might give you the equations, but they'll not give you diagram, okay?
Okay.
So once you read the question, it's a very good point. Once you read the question, sketch the diagram. That is the first step.
Okay.
Once you sketch the diagram, then you do the rest, which is, I'm saying let PQRS be the inscribed rectangle where PXY is any general point on the semicircle, right? Then define all your points. And then you say, well, my rectangle is PQRS and the area is 2x times y. Since my length now is from R to S, which is x plus x, 2x.
Yeah.
And my width is this much, right? So y, correct? So we got this. Now, you could do implicit differentiation at this stage, but if you have not learned that, then in that case, it is a good idea to isolate your variables. So you know that the equation of a circle is x squared plus y squared equals to 10 squared. Isolate y, which is square root of 100 minus x squared, right? A positive
Mhm.
value, since we have a semicircle where values are more than 0, positive values. Substitute that value to get expression of y, a, in terms of x, right? So we substitute y value, square root of 100 minus x squared, and we have a, area of the rectangle, as 2x times square root of 100 minus x squared, correct?
Yeah.
Now you can find the derivative, apply the product rule. So at this stage, apply the product rule. So we get derivative of 2x, which is here, times that other function, plus 2x times derivative of the other function. And here we have the derivatives. Perfect.
Yeah.
You will write minus half there and then do all this. But
Oh, yeah.
this page, try to do it direct as we have done, okay?
Yeah.
And then you simplify this, taking this as your common denominator. When you multiply the square root term, the square root will vanish and you'll get 100 minus x squared without square root. Is that clear?
Yeah.
Common denominator of 100 minus x squared. And that is your result for the derivative of a, the gradient a with respect to x. That is to say, area of this rectangle basically depends on what x you took, right?
Yeah.
And that is the gradient. Our critical number is when we make this 0, the numerator 0, that is our critical number. And that is most of the case stationary points, because if it is not defined, then in real life situation, that is not a solution. Is that clear? Most of the time. But it could be an absolute function also. In that case, the critical number is very important, correct? So most of the time they use stationary points or stationary, that works fine. But critical number, again, I will say, is a general term which should be used, okay?
All right. Okay.
Now, so you could take the value which is numerator is 0. So numerator 0 gives you the answer. Sorry. Oh, here we have done. So we have saying that the critical number is 0 means the numerator is 0. That gives you the x value is 5 square root 2. Perfect.
Uh.
So 0 equals to 200 minus 4x squared. So bring 4x squared to this side, divide 200 by 4, and then square root.
Yeah. Yeah. Why? Wait. We're doing this because we need to find the critical number.
Yes.
Okay.
So the idea here is, in a closed interval, you understand that the maximum or absolute minimum occurs either at the endpoints. So we already have the endpoints minus 10 and plus 10,
Oh.
or at the turning points, or the local maximum minimum, which is at the critical number. So here we have one critical number in our domain, which is square root of 50. X equals to this value, right? Is that clear? Well, actually, strictly speaking, in this particular case, there are two thoughts about it. We could do plus and minus also when you do square root. Is that clear to you? So you'll get plus and minus value. But when you're
Yeah.
talking
So.
about area and all, area is always an absolute value, so you can make an absolute value, correct? So without
All right.
complicating further, we'll just assume x to be a positive value at this stage.
Wait. How come we can't do root 100 square root 100 minus x squared equals 0?
You can do, yes. That is also a critical number, and that will give you plus and minus 10 as your answer.
Oh.
That is correct.
Oh. Which are the endpoints? Okay.
They are the endpoints. So in this case, they are the endpoint, yes. So critical number, take both. Okay.
Oh, okay.
And here, since we have defined x as within plus and minus, you could actually take plus and minus.
Oh, okay.
and you'll get plus and minus here. So as you can see from the symmetry, we could have selected a point this side also. It makes sense.
Yeah.
Correct? So that will also work for you. Fine. So either way, you get your critical number. Now the idea is substitute the value and find the area for all the 3 points. The 3 points are the boundary condition, minus 10 and plus 10. So find the value of area at minus 10, find the value of area at plus 10. Okay, area formula is given here.
Yeah.
As soon as you plug in minus or plus 10, you get area of 0. So that is a minimal area. I mean, you are interested in maximum area, correct?
Yeah.
So you got extreme values giving you minimal area of 0. And when you substitute the other critical number, you get area of 100. So you know the maximum area should be 100. That's your answer.
Oh.
So we did
Okay.
not analyze the situation using first and second derivative. You get the idea.
Yeah.
Much, much simpler. It gives you a result and makes sense because it is a continuous function within a restricted domain. So all the turning points we have considered, correct? Well, the turning point could be plus or minus, but at the end, when you write the dimensions, for example, or you write
Yeah.
the area is always positive, dimensions are always positive. Is that clear to you?
Yeah.
So in that case, it'll be a positive term.
When we were finding the derivative of the area, didn't we do like the first derivative?
Yeah, but we never analyzed it. We did the first derivative because we need to find the critical point.
Oh, right. Okay.
Right? So let's try to understand again the concept. Our absolute value could also be at these points, local points. Do you understand?
Yeah.
Depending
Yeah.
on where the endpoints are. You know, if the endpoints are like, let's say this place, then this local minimum is also absolute minimum.
Oh, right. Okay.
So
Yeah.
therefore, we need to analyze the critical points where we have the turning points or the derivative is not defined, and also the endpoints. Is that
That
clear?
makes sense. Yeah.
So that is why we did the first derivative. The idea was to find the critical number and don't analyze it further. Just find the value at that point. What is the value at this critical number? Substitute and then find the value. We say, well, when I substitute, I get a value which is more than 0, which is 100 in this case. And this 100 is more than the other two values which we found. So it is the maximum value. That's our answer.
That makes sense.
You get the idea?
Yeah.
So optimization questions are very complicated as such. You have to make a sketch. We have to analyze what kind of variables could be there, what could be the restrictions, then work it out. And this, you have a restricted domain as we have seen here. You may actually avoid few steps of analyzing the first and second derivatives and get to the answer much faster using extreme value theorem.
All right.
You get, it's a very effective tool. So, Amy, can you summarize what you've learned here?
Yeah. So, what, for this question or just overall?
Okay, let's go with this question first.
Okay. So what you've said is, so in the previous slides, we found the extreme values using the first derivative. However, in this case, first or second derivative, but in this case, we can do it without using the first or second derivative because it's much quicker using the extreme value theorem.
Yes.
To do it this way. So obviously, I think we should start by reading the question and doing a quick diagram because that is the key to basically unlocking the whole problem.
Correct.
Yeah. So just knowing, finding all these little equations, like just simply putting a point as x, y, finding that because it's changing y over changing x, now we have easily got the gradient and the radius and everything. So now we know that the point, let's say the radius section is x. Now we know the length of the rectangle is 2x. and then you find the area of the rectangle. So that would just be 2x times y.
Yes.
2xy, yep. And then we know it's a semicircle, so the area of that would be x squared plus y squared equals r squared. And r squared in this case is 10, so we just sub that in, and you get y equals square root 100 minus x squared. Then we found y, so we just sub that in into the 2x y equation,
Perfect.
which is the area of the rectangle. And we get 2x square root 100 minus x squared.
Yeah.
And then we have to find the first derivative of the area in order to just find the critical number.
Yes.
You just need to find the value. So once we find making the first derivative, so we got the first derivative area there, and we need to find the critical numbers. That means f prime x equals 0, or f prime x does not exist.
Correct.
In this case, the does not exist one, which is just the boundary points. So we just kind of left that. But the f,
yes, you have to do it.
You can do it. Yeah, you have to do it, but it would just be the 10 and minus 10. So yeah, okay. And then
that's very good, Amy. Let me also give you one more thing here. Now, because of the symmetry, so whenever you're working in calculus questions, symmetry is a very important thing to understand. In this case, you know, it is very symmetrical. So what you could also do is you could only maximize first quadrant. So that will simplify many terms. So you can think about, well, the whole area will be maximum if the area in the first quadrant is a maximum. Is that clear?
That makes sense, yeah.
Half the area is maximum, then full area is also maximum. Correct?
Yeah.
So therefore, we will take our question here and we'll say, well, in that case, the x value changes from 0 to 10. So the whole question is much, much simpler because you're only working with this particular area.
Oh, so you don't need to deal with the 0 minus 10.
And then you say, well, the extreme values are working from 0 to 10, and then you plug it in, and it's so much simpler. And this confusion which we had of plus and minus, things like that, goes away. Because we are saying now, x is greater than equal to 0. So we are only taking positive values.
That makes sense, yeah.
The thing is, x is also a dimension, and dimensions are not negative. So when you put minus 10, oh my God, that's like confusion.
Yeah.
So, to avoid that, I'll prefer you to redo this particular question, right?
Yeah.
So work with this particular domain and give a reason why you're working like this. If half the area of the rectangle is maximum, then full area is also maximum, correct?
Yeah.
So half the area of this particular and submit your solution, right?
Okay.
That is your first question. Second question is the practice test. Now, this is a very important chapter. Every time in any question paper, you'll definitely have a question where the restricted domain is mentioned. Is that clear to you? Here are 6 questions for you, Amy. I'd like you to take a picture of these 6 questions, try them out. I've given you links for my videos, which will provide you with solutions or hints to solution. In case there is a difficulty, you can check those videos also. Correct?
Okay. Yeah.
So these are very important questions to work with. So I think with that, we come to an end of this particular video. I will now like you to summarize your learnings about this particular unit.
Right. So I think the key thing is when it comes to extreme values, you need to keep 2 things in mind. So number 1 has to be a restricted, a closed interval, where, so when we have square brackets, both of those points, the endpoints are included. Then it has to be a continuous function in order for there to be an absolute maximum or minimum. What we also learned is, so let's just pick like a quadratic, that minimum point can be the local minimum, but it can also be the absolute minimum. Then you, so like in the last question we just saw, if it's given like a worded problem, always start by doing a little diagram of some sort in order for you to help like solve the problem much more easily. When there are cases where you don't have to find the first or second derivative, you can use the extreme value theorem in order to get to the answer quicker. And always find the critical number, which would be f prime x equals 0 or f prime x does not exist. Finding those two values and then sub that into the main equation, the function, and then also the endpoints, you sub those values into the function, and then you got your all your points, and obviously you just, if you're doing absolute maximum, you just find the highest value, absolute minimum, find the lowest value.
Perfect.
That's it.
That is perfectly well said. Now, as another part of this, to summarize this particular unit, you may write down the algorithm of finding absolute maximum and absolute minimum. So the first step is you have to look into the question saying that basic requirement is that the function should be continuous and it should be within a closed interval. That is the first thing. Then only you can do the rest. Then second step is to find the critical number. Critical number will mean that either the derivative is 0 or it is not defined. So now you get few points to test. All the critical numbers, you have to find the value of the function. So substitute the value, critical number x value, into the function to get the value of the function, right? Whenever we are saying maximum, minimum, we are checking the y value, right? Output, the dependent variable. Now, and the other 2 points are always the extreme endpoints. So also substitute the left side and right side extreme values of your interval. So you compare them all. So once you compare them all, from these set of values, the one which gives you the maximum value will be absolute maximum. The one which gives you the minimum value will be your absolute minimum. Is that clear to you?
Yeah.
So that is what it is. And since these values are directly giving you the answer for absolute maximum and minimum, we need not analyze the first and the second derivative.
All right. Okay.
Now, here's a caution. If the question says also write down the local maximum and minimum, you cannot help it. You have to analyze for the local maximum minimum. Perfect.
Yeah.
So for most of the time, when you say optimization, we're actually looking for absolute value.
All right. Okay.
So most of the real life applications are optimization questions where we are looking into absolute values. So you can avoid first and second derivative and save some time using this strategy. The only critical part here could be at times to find the two intervals, closed interval, and relate these terms, right? But once you could do that, it is much, much simpler. Is that right?
So if the closed interval is not given, we would have to figure that out.
If the closed interval is not given, in that case, you cannot find the absolute maximum minimum value.
Yeah.
I mean, you can find, but you cannot be sure that there will always be an absolute maximum and absolute minimum value. So here I should end with saying that in case we have a continuous function within a closed interval, we will always have one value which is absolute maximum and one value which is absolute minimum.
All right.
Is that all clear?
It's perfect.
Perfect. So now another exercise for you is, I had shared with you 6 questions there. They are examination style questions. Wherever possible, you have also learned the technique of implicit differentiation.
Yeah.
Wherever possible, apply implicit differentiation and see whether it works or not for you.
Okay. Yeah.
Okay.
Perfect. Thank you so much, sir.
Bye.
Have a good rest of your day.
You too. Thank you.
Thank you.